Welcome to Middle School Physics Episode 3, the only show that uses bad memes to teach 6th graders physics. Today we will be talking about Newton's first law. Once again, this is our third episode. If you guys have any questions so far, go ahead and email me. It'll be in the description. It's just middleschoolphysicshelp@gmail.com. So obviously, since they're Newton's law, they are made by Newton. No, not that one. Here, give me a minute. Not that one either. This one. Isaac Newton, this guy right here. So rumor has it that an apple fell on his head and he developed the Newton's laws. Again, this is just a myth, but it's a pretty awesome story. He also did invent calculus at age 26. So the next time you think your math homework is hard, imagine inventing calculus. So let's dive straight into the topic. So Newton's first law has a set definition. It's been varied quite a bit, so I'm going to give two of the most popular ones that I just found on the web, and these are the ones that seem the most helpful to me. So the first one is Newton's first law of motion / the law of inertia, which it's sometimes called. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So most of this makes sense. It's just this acted upon by an unbalanced force part that we sort of don't understand. So pretty much what it is saying is the behavior of all objects. So all objects tend to keep on doing what they're already doing, whether they're at rest. So if they're at rest, the object wants to stay at rest. If it's in motion, it wants to stay in motion, unless acted upon by an unbalanced force. What is an unbalanced force? We'll get into this later, but it's just a force that is not equal to 0. So if an object's at rest and I throw a force on it or I push it, that means that the object will start moving because I've just acted an unbalanced force on it. Now, force is another definition that gets pushed around quite a bit. Oh, that's ironic, no pun intended. But the definition for a force is simply a push or a pull. So push or a. So anytime we exert any force on an object at rest or already in motion, either it'll stop or continue what it's doing, or we'll move it in some sense. So Newton's first law is sometimes called the law of inertia. Why would it be called the law of inertia? First, let's define inertia. Inertia is a property of matter by which it continues in its existing state of rest or uniform motion in a straight line, unless that change is changed by an external force.
What is that? What is that? Wait!
Yep, he's back. Let's go ahead and simplify this. So inertia, a property of matter. That just means it's a trait of how any object acts, by which it continues in its existing state of rest or uniform motion. That just means that the object will either stay at rest or motion in a straight line unless that state is changed by an external force. So pretty much what this means, it's almost a trait. It's a trait of laziness. It's a trait of how much an object wants to move, how much it wants to change its position. It won't change its position unless that state is changed by an external force, which we just read a couple of minutes ago, which must be an unbalanced external force. External just means outside, so out, I'm going to go ahead and write out here. So one last note that we want to put with inertia. Inertia is directly proportional with mass. That means the more mass there is, the more inertia there is. So directly proportional is another math term. I haven't learned this in math class personally, but I probably will this year. So what it means is that if one of, let's say, constant changes, another constant will be affected by it in some way. When they're directly proportional, that means if one constant, in this case mass, goes up, in that constant, inertia, we'll just draw a star for inertia, will also go up. So they're directly proportional. You can find this out by taking two thumbs, throwing them up, directly proportional, inversely proportional, which we'll get into in the next law. So let's review our unbalanced versus balanced forces. So as we established earlier, An unbalanced force is a force that is not equivalent to zero. So I'm just going to give some examples on that. Let me disappear real quickly. So one example of an unbalanced force is if we have a nice little table. Now on that table, we have a purple book. It's a comic book, and it's a comic book about Isaac Newton and his laws. So it's a nice book. So this book is at rest. So this means that there is a balanced force acting on it. Even though you can't see it, there are multiple forces acting on this book. The first one is surface force. Surface force is the force that is keeping the book flat on this table. It is pushing the book up. So practically the table is pushing the book up. Now there's another force. The force of gravity. Now, this is pushing the book down. So both of these forces cancel each other out. So let's say this force is at 10 newtons. This force is at 10 newtons. When we subtract these two, we end up with 0 newton. So that's just an unbalanced force. That's what an unbalanced force would look like. Now we know what a balanced force looks like, but what about an unbalanced force? Easy. So, I don't know what I'm doing. Let's say we have our book again, except someone's really angry and they have thrown the book. Perfect. So now the book is moving quite quickly in this direction. It's moving with the force of 3 newtons. That right there is an unbalanced force. So to end this video, I'm going to give a couple of real-life applications because we've covered all the technicals of it, all of the definitions. If there was a formula, we would have covered that, but there's no formula. So I'm just going to give a couple of applications. So a really famous one is to prove Newton's first law. Is if you were in space. So this is the little picture of space. Let me get some. These are stars. I'm sorry, I'm really bad. This was a bad idea. So you're in space, and you bring a little ball with you. And you kick it, or you throw it, or whatever. According to Newton's first law, it will stay in motion in a straight line at the same speed forever, with no end. If you did this on Earth, there would be multiple forces stopping the ball. Like gravity would be pushing you down, air resistance would be pushing against the ball. But if we were to do this in space, it would go on forever and ever at the same velocity, in the same direction, at the same speed. Another example here on Earth is almost a frictionless example, is when you take a hockey puck and you slide it on ice. So you're playing ice hockey. So we go ahead and slide our puck. What would happen? Well, the ice is almost frictionless because it has almost no friction because it's a very slick surface. So the puck for a very long time would go in the same distance and same speed for a while. But eventually it would have to slow down because we're still on Earth. So the last example I'm going to give is probably the most important one, would be the addition of seatbelts. So imagine you're driving quite quickly with the car, and once again, you're going to hit a wall. So you're driving quite quickly, like into a brick wall or a tree, any solid object. The car will come to an instant stop, so the car automatically stops, but you will keep moving. This is because the force is acting on the car, not you. So when the car itself stops, your body doesn't want to change. It wants to stay in motion, as the first law suggests. So then your body will crash through the windshield, and you will end up dying. That's why seatbelts were invented. Because of the first law, your body is not affected by the force, because it's staying in motion. No force has affected it directly. Force has affected the car, but not you. This led to the invention of seatbelts. This is why Newton's first law is important. Until the next episode, don't be changing, and as Cam Newton would say, dab on 'em.